Now, if we have a thick wire and a thin wire, both of them we're cranking at a rate that gives us a 5 joule per coulomb or a 5 volt potential difference from one end of the wire to another. And let's assume equal lengths of wire also, because the length of the wire enters into this whole thing. Okay, if we have the thick wire, and assuming again that the wires are of the same material, the thick wire is then therefore going to have more charge carriers, in this case more electrons available, which implies greater current. There's a greater current in this wire than there is in this wire. Now, if there's a greater current, that means there are more electrons flowing past a point at a given time. They're going to be flowing at the same rate in this wire as in this wire. That is, they're going to be moving at the same average velocity in this wire as in this wire, because each electron has the same energy difference between one end of the wire and the other, meaning it has the same energy difference over every small distance, and therefore picks up a certain amount of energy every small distance it travels. Excuse me. A given electron is going to feel the same in this wire as it does in this wire. It's just that there are more electrons here than there are here. The electrons in this wire behave the same way they do in this wire, same velocities and so forth, because, again, of this same energy difference between the ends. And they encounter the same molecular densities and so forth. So everything's the same for every electron in these two wires. However, this wire has more electrons, therefore there's a greater current, and those electrons are going to interact with more atoms or molecules, depending on what the wire is made of, and give up more kinetic energy because there are more of them. Each electron will give up the same amount of kinetic energy here as an electron down here, but there are more electrons, so they give up more kinetic energy, which means it requires more power to crank the generator. Now, it turns out that this number is determined just by the cranking rate, so we're cranking both wires, we're cranking around at the same rate, okay, the same angular velocity of the crank. Since we need more energy here, that means we're going to have to use greater force at the generator for this wire than for this wire. Again, we would say that this wire has less resistance to current flow than this wire because there are more electrons available to carry the current. So that the wire with the lesser resistance will carry the greater current and require more power, and therefore more force at the generator. We can also look at what happens if we have wires of the same composition and the same diameter. I haven't really been specific, but let's assume that these wires have the same diameter, and the only difference is that one's longer than the other. We keep the same potential difference, the same voltage across both wires. That is, we crank the generator at the same rate on both wires. However, in the shorter wire, we get a greater potential gradient, which means more volts per meter. Okay, potential gradient or voltage gradient is just the voltage per unit of distance. So we have a greater voltage gradient, which means that the electrons here will be accelerated at a greater rate than the electrons here. That means, essentially, that the electrons here will make more collisions than the electrons here. And they'll also, on the average, move faster, as we said. So you're going to have more current here and more frequent collisions. Both more current and more frequent collisions here, it turns out. So you have a greater acceleration of the charge carries greater current. However, there's another factor here that we need to balance with that. Now, there are more charge carriers involved here, and it would seem that that would tend to give us more current. And later on we're going to have to look at why that isn't really, I mean, that's a factor, but this is a greater factor. Okay, the greater acceleration turns out to be increase the current flow, or the number of charges flowing past a point, in proportion to the inverse square of the length of the wire, whereas this is only proportional to the length of the wire. So you have these two proportionalities fighting, and this one turns out to win. But you have to take into account the fact that here in the longer wire you do have more charge carriers. So the argument is not as simple as the argument that we see in red. There is another factor here.